lunch, so I'll try to be quick on this. This is a very nuts and bolts talk about our experiences at Oakridge in accepting and using our Minsky system, Power 8+. We took delivery of the system late last calendar year, and it's a 3-cabinet, 54-node Minsky-based system. And the primary purpose of this system is for us to prepare our applications for the Summit system, which will be coming, actually it's beginning to be delivered even now to Oakridge. Summit will deliver 200 petaflops of performance, and since NVIDIA has announced that the Volta GPUs will deliver 120 teraflops each of half-precision performance, we will basically have a 3.2 exaflop system for mixed precision computation, which we expect will be the largest machine learning system in the world. This is just a slide to show a little bit about the status of Summit. I believe now we have all of the cabinets delivered to Oakridge and installed. They're empty cabinets. We're still waiting for the processor boards to come in. And also the fiber optic cables are being installed. That's partly done and it's in progress right now. And so we hope early in 2018 to have the entire system delivered. We'll start working on it, trying out our codes on it, and drive toward acceptance of the system later on in 2018. This slide shows a little bit of context here. We've been progressively deploying larger and larger systems over time. Jaguar was a 2.3 petaflop system, and then the next step after that was Titan, which was a 27 petaflop system. It was the first GPU-based system that we deployed, and actually the second one ever deployed, large-scale HPC system after the Roadrunner system at Los Alamos. Summit will be 5 to 10 times more powerful than Titan, and we're trying to drive toward getting an exascale system in roughly the 2022 timeframe, which we're hopeful of. So about Summitdev. It's basically got 3 cabinets. We originally requested 2 cabinets with 36 nodes, but we decided to get a 3rd cabinet to help support projects from the xScale computing project. Each compute node has 2 IBM Power 8 CPUs. Each one has 10 cores with hyper-threading, and also there are on each node 4 NVIDIA P100 GPUs and a little over 5 teraflops of double precision performance each, and also they're equipped with the NVLink and also 16 gigabytes of HBM memory on socket. And also we have the Mellanox EDR InfiniBand, and we also have NVMe disks on each node to experiment with workflow and I/O using those. So for today I'd like to talk about 2 things. First of all, some of the results from our acceptance process to show some of the performance results on the system and experiences, and also subsequent benchmark we've done to sort of like rerun some of those cases after acceptance last December. And also I'd like to give some very recent results with our early application readiness effort to get codes running very efficiently on Summitdev in preparation for Summit. So we received the system originally in October of 2016, and we performed acceptance testing and accepted the system in December. Acceptance testing is a process we've used many times with new systems to try to validate the hardware and software of the systems to make sure that they are ready for our users. We perform a battery of tests to evaluate all aspects of the system that we receive, and we've have several papers in the past regarding this process, and the latest one presenting at IWAF last summer, which has many of the results that are presented in this talk today. We go through several stages. We have basic hardware tests to turn the machine off and on again and make sure the actual hardware is running. I/O system tests, where we have various tests to test the I/O system, its speed and performance and reliability. Functionality tests to make sure that the software does what it's supposed to do. Performance tests, where we measure performance of kernels and applications to make sure that they hit the required targets. And then finally, stability tests, where we run a mixed workload representative of typical user workloads over a period of time, for example, 2 weeks, to make sure that the system is stable. Our software tests, here are some of the software tests we performed. We performed low-level tests, benchmarks of the hardware. We run tests of the compilers to make sure that they're running okay. We have a set of core benchmarks. There are 13 applications that IBM and the other vendors are contractually required to hit certain performance targets for these applications, so we test those. We have Miniapps and also OLCF applications, which are representative of our workload at Oakridge. This is a chart. It's very busy here, but it's to show that we think about testing different aspects of the system. In the left column here, we have different compiler families, languages, OpenMP, OpenACC, MPI, ESSL, various libraries and software features. And along the top, we have the different codes that we use for testing. So we try to cover everything as much as possible with using the codes that we've selected. We ran our first test shots in November, experimental runs to get ready for the acceptance tests. We didn't run a formal performance test to actually collect performance data, but I will be presenting some performance results today. We will perform very rigorous performance tests for Summit because there will be contractual requirements that system meet the targets. So I just want to give a little bit of our experiences really on the ground in terms of running acceptance. We encountered some early hardware problems. This is often the case as we get brand new systems with brand new hardware. Sometimes the first hardware or some of the first hardware off the assembly line, we identified problems often, and we did in this case. For example, there were 2 nodes that had GPUs for which the GPU direct was not properly working, so we had to have someone come in and replace those. We had to do a thorough suite of tests to be able to identify these problems. Also, we used beta software, which is a little bit unusual, but some of the software we used was beta software because the release software wasn't ready yet, but by agreement we decided that we would use the beta software, and in January that was upgraded to the GA software. It was basically a matter of scheduling. We just wanted to get a more or less working software stack on this system so our application readiness early users could use the system as quickly as possible. We performed many tests of the GPUs. A lot of these derive from the CUDA toolkit. GPU Direct, NVLink, Unified Virtual Memory Addressing, MPS, CUDA Fortran, Managed Memory, and we had identified some issues that were small issues that were fixed during that time period. Here's a performance test. This is for the NVLink performance. The theoretical peak was 160 gigabytes per second. In this graph, you have on the y-axis the megabytes per second of transfer speed, and on the x-axis is the message size, or basically the data item size. And 160 gigabytes per second peak, and we attained about 120 in practice, and so about 75%. This is similar to what we obtained on Titan for PCIe 2 transfers. So we were satisfied with this level of performance. Also, we tested MPI performance with the IMB benchmark. Basically, the peaks are 50 gigabytes per second, bidirectional, 25 for the unidirectional, and the figures we actually measured were 39 and 22. And so this graph again shows on the x-axis is the message size, the y-axis is the message rate. So we obtained results that obviously we can't attain peak speed, those are just theoretical numbers, but we were satisfied with the level of performance we got for the transfers over the network. We tested 4 compiler suites, XL compilers from IBM, PGI compilers, GNU compilers, and LLVM. Some of the compiler functionality is very new. For example, XL, being a new partner with NVIDIA, came on board with supporting CUDA, Fortran, and now OpenMP 4.5 as that standard has been finalized. PGI is, through this partnership, supporting a power processor. LLVM, new support for Fortran and OpenMP 4.5, and GNU has also begun to support OpenACC. And so we expected there to be potential problems which we were going to evaluate. We used standard compiler test suites to validate performance. For example, here's some results for OpenMP 3.1 validation suite. LLVM beta compiler had the highest failure rate, and there's some tests which were failed by all the compilers, leading us to suspect that there might be a bug in the test suite, though I don't know if we've explored that in depth quite yet. This is another set of tests. This is from the Coral Benchmark Suite. These are the 13 applications that the vendors are required to optimize for the target hardware. And there's a contractual requirement for them to hit the targets. For this acceptance, we tested three different codes, NEC 5000, which is spectral finite element code, HackMK, which is the microkernel from the cosmology code, Hack, and QBox, which is a molecular dynamics code. They all ran successfully, and we did collect this strong scaling performance graph. It's for a small problem up to over 32 MPI ranks here, and it scaled reasonably well. There is some turnover for a larger number of ranks, but we'd expect this for a smaller problem. ScaLAPACK test, one of our early application readiness codes requires ScaLAPACK, so we put this in the mix and tested ScaLAPACK for different compilers, and you can actually run ScaLAPACK. One thing is PGI supplies its own version of ScaLAPACK, but usually we would use the one you can download from the internet, and then you can use it as a backing library for the BLAS calls. You can either use the standard LAPACK library or use ESSL, and so we tested all these, and they all passed tests except for LLVM, which is new and it's still in beta form. Here's another code. It's a Miniapp taken from the de novo radiation transport code. We got a similar performance in terms of percent of peak flop rate as we get on Titan, so we were happy with that. This is another test of dense linear algebra. Since there's so many compilers, languages, and different versions, we have ESSL we can use to do dense linear algebra, LAPACK, which we compile, OpenBLAS, Magma. So many combinations were tested here. Not every combination, but many of them, and these all passed successfully. I think this is a challenge of the system. There's so many combinations that we need to give some careful thought as developers as to how to select which compiler, etc. to use. Here's some benchmark results for the, essentially this is a matrix triple product of 3 matrices, and this is a dense linear algebra DGEM test. The two lines at the top show that for the P100 peak double precision flop rate and the peak DGEM rate, which we got from some of the NVIDIA information. And down here are the flop rates as a function of matrix dimension along the bottom here. They underperform the theoretical peaks mainly because the transfer of data to and from the GPU is also counted here, which ideally will be useful to overlap those. And basically, so OpenACC with the CUDA BLAS gave the best performance. ESSL is new to supporting CUDA, and that wasn't quite as good, but it's still in development. XRay trace is a ray propagation code to simulate X-ray lasers. Collected some data from this, and all the compilers and combinations of a programming model performed well, except for unknown reasons, PGI and OpenMP version underperformed. We're not sure why this is, because other codes are able to use PGI with OpenMP effectively. This is GTC. It's a fusion code. We ran this, and these are just some weak scaling, roughly weak scaling results. There is some growth in the runtime as you increase the number of processes, but we kind of expect this because it's kind of a characteristic of the code, so it was expected behavior. Some of our observations from the process, we felt that the issues were very proactively fixed by the vendors. We kept a bug list and worked this with the vendors, and they fixed the problems. Overall, it's a very powerful system. The GPU flop rate is 4 times that of Titan, which is an old Kepler K20X GPU. It's often straightforward to get codes running on that system from another system, but it may take significant efforts to actually do code tuning to get high performance. We carefully tested the early hardware, and we had to pay attention to interoperability issues between compilers and libraries. For example, using ESSL SMP version with a PGI compiler that uses OpenMP otherwise is problematic because they use different runtimes. So there are various combinations that one has to stay aware of. There's some other differences. For example, the default of char in C and C++, whether that defaults to assigned or an unsigned, which is based on whether it's Power or x86. And obviously, different compilers and different hardware require different compiler flags for optimization. And also, the different programming models, as I mentioned, have different levels of maturity. Continued need for vendors to fix compiler bugs. We're currently getting new beta drops of compilers, and so we work the issues with the vendors as we find issues with them. We're waiting for all the software to use the NVRAM on each node, which will greatly help our I/O. So we're waiting on that. And also, as I mentioned, making the different choices of not only compilers, but also how to run on a node, how to manage the CPU threads, the NUMA domain issues, how many MPI ranks per node to run. We're commonly having essentially one MPI rank matched with a single GPU for the most part. And also performance portability. We'd like all of our codes to run on different other platforms because a lot of our users don't only run at Oakridge, they run at other centers also, and so users are looking for strategies for performance portability. OpenMP 4.5 and similar approaches are promising in this regard. I just wanted to end with a few slides on our application readiness effort. This concerns CAR, the Center for Accelerated Application Readiness, which we started with Titan. And this is an effort mainly to port application codes to next generation systems. And we have a team of people dedicated to this. I wanted to give a few results of work in progress for some of these codes. This is a list of the codes. We have 13 applications listed along the left here, and these are different from the Coral codes. These are codes that we selected that are important to our center. They span a variety of science domains: climate, chemistry, astrophysics, etc. And each of these codes is assigned a local liaison to assist with the porting effort, in addition to the code PI's team. So just want to give a few results. Spec FEM3D, which is a finite element code that is used for seismic modeling. So far, it has gotten a factor of 2.15x faster than Titan on a GPU to GPU basis. Now, for comparison, if you compare the K20X GPUs to the P100, the P100s have 3 times the memory bandwidth and 4 times the peak flop rate. So what we're aiming at is hopefully 3 to 4x performance improvement coming off of Titan. So this is a memory-bound code, so we would expect around 3x performance, and currently we've gotten 2x, and this is just a work in progress, continuing to improve that. This is for the GTC code. It's a fusion code used for modeling fusion reactors, and this code has gone through a number of revisions. It's currently getting a 3x speed up compared to Titan, GPU to GPU, and we've been able to use the new NVIDIA AMGX linear solver library, which very efficiently uses the GPUs, and this has been very helpful to us. And finally, QMCPAC, 20 on a node-to-node basis for Titan, compared to Titan, it's a 20x faster than a Titan node, and on a GPU to GPU basis, this translates to 5x faster on the P100 GPUs, and this is even above the 4x flop rate improvement. So they apparently have done some additional optimizations to the code over this project. So it's been very successful. And so in summary, we're very pleased with this system. It's a step up in performance from Titan, and we can immediately notice that speed as we're running applications. It's only 54 compute nodes, but it's nearly 1 petaflop of performance. Programming is more complex. There are various choices, not just for this system, but in general, as the compute nodes become more complex and have multiple levels of memory. Managing this is a challenge, and depends on the specific application, how to optimize for that. And we expect, as we get more Summit hardware very soon, that we expect even higher performance. So that's all I have. I'll take any questions.
Have you done any benchmarking with any of the deep learning frameworks?
We have basically TensorFlow running in container. Some people are actually running it multi-node at Oakridge on Titan. We do have a test on an acceptance test on Summit using TensorFlow. So yes, we're getting ready for that. Yes.
This may be a tough question, but have you looked at the network utilization of Titan compared to Summit? Where on Titan you have a single GPU per node with Gemini interconnect, and then on Titan you have on Summit you have a lot of GPUs with an IB interconnect. Do you see saturation of the bandwidth?
Well, we are concerned that the bandwidth is, the flop rate is growing faster than the bandwidth. Definitely concerned about that. Turned out that the actual Coral applications, the way they were set up, for whatever reason, they didn't tax the bandwidth so much as some. There were no 3D FFTs or very very heavily bandwidth intensive applications. And I think part of the reason is that I think users are simply have kind of migrated or tried to migrate against some of the applications that are very bandwidth limited, simply because we know it's a challenge going forward for the bandwidth to keep up with the growing flop rate on the node. We haven't actually measured per se, but we know it's an issue. Everybody's like looking at their code to see how to deal with that overlap, computation with communications, and various things like that. So.
Is the 5x expected performance based on LinPack?
Actually for 4x, that was basically based on peak flop rates. 5.2 for the Pascal, 5.2 teraflops, and the K20X was 1.311 teraflops. So it's simply 4x from that. And actually the degen performance is pretty close to that. It's not 100%, but it's very high.
Talked about the LLVM having a high failure rate. Can you say more about that? Is that more specific to the Fortran or the what?
I'm not super familiar with it. There are other people on the team who deal with that, but basically we have LLVM. The code we ran was, I understand, the XLF front end of the XLF Fortran compiler was connected to LLVM backend, and so that's how we got Fortran codes to Any other questions?